Hello and welcome back everyone to the Exam Tomorrow series lecture 4 differential equations. So in this video we are going to talk about differential equations of first order but higher degrees. So let us take a look at how things are going to be. First order and higher degree, a differential equation looks something like this, where you can see every derivative is of the first order, dy dx, dy dx, dy dx and so on. Everything, all the derivatives are having first order. But the powers of the derivatives are higher, which means the power is more than 1. Okay. So definitely this is becoming non-linear in nature. It's a non-linear differential equation. And the coefficients a1, a2, an, these can be any variables x, y. Okay. So that means we are basically dealing with non-linear differential equation, which is involving first order of derivatives and higher degree terms. Okay, so now this can be distributed into 3 categories. Okay, so we'll be solving this in 3 categories. The first category is solvable for P. Achha, now what is P? From now on, whenever we write something as P symbolizes dy dx. Okay, so P means dy dx in this entire course of differential equation, which we are going to deal with. Involving this video, the upcoming video, everywhere P would mean dy dx. Okay. So either the differential equation is going to be solvable for P, that means solvable for the derivative dy dx. This means that this differential equation can be expressed in this format, that dy dx can be separated on one side and on the other side we will have only some function of x and y remaining. No derivative will be there on the right side. If we are able to arrange the differential equation in this format, then we are going to say that it is solvable for P. Similarly, it will be solvable for Y if we can keep Y on one side and X and P on the other side. Okay, and in the same way it will be solvable for X if X can be kept on one side and some function of Y and P on the other side. So depending on how we can arrange this differential equation among these 3 categories, we are going to call them solvable for P, solvable for Y and solvable for X, and each of them will have a different style of solving. So let's get started with our first category, which is solvable for P. Let's take a look at the differential equation. So we're going to solve something like this. It will not be mentioned whether you have to solve it for P or X or Y. It will be just asked to solve. You have to figure out whether it is solvable for P, X or Y. Now how to understand that? In this question, first of all, we'll replace the dy dx with a P. So it's going to look something like this. Now we can see over here that we can keep P on one side and we can take everything else, that is function of x and y, on the right side. That means we are able to arrange this in the format P as a function of xy, which looks exactly like this, P as a function of xy. That means the given question must be solvable for P. Okay. So this is how we understand whether a given differential equation, it is solvable for P or X or Y, and then we proceed accordingly. So once we have understood that this is solvable for P, the process for solving it would be, we don't need to replace dy dx with a P for this case. We'll just try to separate out X and Y. Okay, so X dy dx equals x square y square minus y. So we would be having dy dx equals xy square minus y upon x, and dy dx plus y by x equals xy square. So over here we can see this is basically looking like a Bernoulli's differential equation. Like if you refer back to lecture number 3, okay, this is nothing but Bernoulli's differential equation, and we need to divide by y square on both sides, substitute it and try to solve it, right? So what we are doing in solvable for P is that if the question involves P, we will be replacing it with dy dx, try to separate out the x and y terms and then try to integrate them. So here we can see we are not being able to separate it in a way so that we can integrate both sides, but what we can observe is it is fitting into Bernoulli's differential equation format, right? So we are going to divide by a y square on both sides. So we are going to be left with 1 by y square dy dx plus 1 by xy equals x. So I have divided by a y square on both sides. Now I can substitute 1 upon y as z, right? So if I do that, 1 upon y equals z, that would mean minus 1 by y square dy dx equals dz dx. So 1 upon y square dy dx, that would be minus of dz dx. So now I can substitute this for the very first term, which is right over here. 1 upon y square dy dx, I can substitute it as minus dz dx. So the moment I do that, minus dz dx, in place of 1 by y, I should be writing z, so plus z by x equals x. Multiplying by a minus sign so that I can get rid of the minus sign at the starting. So dz dx minus z upon x equals minus x, right? So now I can say this is a linear differential equation and this is linear in z, right? So linear in z, that means I will get the integrating factor out of this. So I can say over here that the integrating factor would be e to the power integration, the coefficient of z, that's basically the capital P term for the linear differential equation. You can refer this back to lecture number 3. So minus 1 upon x dx, right? So that would be e to the power minus log x, and that would be ultimately 1 upon x, right? So 1 upon x is our integrating factor. Now directly we can solve this. The direct formula for solving this was z into integrating factor is equals integration of the right side into integrating factor. Right side is minus x, so minus x into integrating factor dx, right? This was the direct format of the solution. So from here I would get z into integrating factor, so z upon x equals integration of minus dx. Now z means 1 upon y from the substitution, so 1 by xy equals minus x plus c. So this will be our answer to the given differential equation. Okay. So let's take a look at another question. First of all, you have to figure out whether this is solvable for p, x or y. So to do that, first let's substitute p in place of the derivative dy dx. So we have p minus, this is dx dy, so that means it's reciprocal of p, 1 upon p. If I do LCM on the right side, I would get x square minus y square upon xy, right? So if I do a simplification on the left side as well, I'll be having p square minus 1 upon p equals x square minus y square upon xy. So now if I multiply the p on both sides, I would get something like this. Then if I rearrange the terms, p square xy minus p times x square minus y square minus xy equals 0. So this is basically a quadratic equation in terms of p, right? P square, p, and there is no p term in the last xy. So that means I can visualize this as a quadratic of p. If I do that, then either I can factorize this, or if I am unable to factorize, I can solve it using Sridharacharya method. In any case, I'll be able to write p as some function of xy, right? The moment I'm able to do that, so I'll understand that this differential equation is going to be solvable for p. Okay. So what we can do is we can continue this process of simplification. We can express it in terms p in terms of f of xy, and then we can maybe separate out the x and y. Okay, so either we should be able to factorize this equation directly, or if not, we have to use Sridhar-Acharya method. So let's see whether we can factorize this. So we have p square xy minus px square plus py square minus xy equals 0. From these two terms, let's try to take px common. So if we do that, we are left with py minus x. From the next two terms, if we take a y common, so we have py minus x. So that means we are able to factorize this. So that means we are going to have two factors separately equals to 0. We have to solve them separately and then again bring them back to get the general solution. Okay, so from here we have two factors, px plus y equals 0 and py minus x equals 0. So we have to solve both of them simultaneously. Now solving the first case, I'm replacing p as dy dx again. So dy dx times x equals minus y. So that means dy upon y equals minus dx upon x, and now I can integrate this both sides. Okay, so for now I am not doing anything with this part. I'm just concentrating on the first part. So if I integrate this, I'm going to have log y equals minus log x. Since we are having all the terms as log terms, so let's take the constant as log c1. Okay, so that I can easily get rid of the logs. So I have basically log y equals log c1 upon x, right? If I combine the two logarithmic terms over there, and I can remove the logs, and I'll have y equals c1 upon x. That means xy equals c1, which is a constant. Now I will concentrate on solving this part again. So let's solve that part, which is py minus x equals 0. So again I'm replacing p as dy dx. So y dy dx equals x. That means y dy equals x dx, and I can integrate this both sides. Y square upon 2 equals x square upon 2. I can write the constant as c2 upon 2 so that I can easily get rid of the 2's, right? It's just a way of simplifying things. So I can get rid of the 2's, and I'm left with y square minus x square minus c2 equals 0. So here also I would prefer to bring the constant on one side. So xy minus c1 equals 0. So now if I combine up these two solutions together, my general solution would be, I just have to take the product of these two terms, because remember we were actually working with the product of the two factors. We solved them separately. The final answer, again we have to take the product of that. But let's keep in mind, here we are having first order derivative. That means when we are solving it, we should have exactly one constant and not more than one constant. So here while solving, we have written one constant as c1, one constant as c2, but while writing the final answer, we need to replace the constants with just one particular constant. Okay, so from here our final solution would be xy minus c multiplied with the other factor y square minus x square minus c equals 0, and that's our final answer. Okay, so we need to make sure we are replacing the constants with just one single constant, right? Because we are solving a differential equation of first order, so there should be just one constant, right? So this is how we are solving differential equations which are in the form of solvable for p. Let's take a look at another differential equation. Here, if you observe, it's going to be difficult if you try to solve this for p, because p is having a very higher power over here. There is again one power of p, and on this term there is no p at all. So that means trying to express this as p as function of xy, this is really difficult because we won't be able to factorize anything. So that means it's not going to be solvable for p. So now let's try to see whether we can express y as a function of the other two variables or x as a function of other two variables. Here actually we can do both. It's already in the form of y as a function of xp. It's already in that format. But if someone wants, then they can treat this as a quadratic in terms of x, then either factorize or use Sridhar-Acharya formula to express this in the format y as a function of x as a function of y and p. That's also possible. So we can solve this differential equation in both ways, but we will always prefer the one which is more easier to do. Obviously this is not going to be easier in this case because it's a quadratic for x, then again factorizing it or using Sridhar-Acharya, that's a few steps extra. Here it's already in the format of y is a function of x and p, so that would be an easier way to solve this differential equation. Okay, so we are going to treat this as y as a function of x and p, that means solvable for y. Now the method for solving this kind of a differential equation is, just remember it this way: if it is solvable for y, you need to differentiate it with respect to x and then proceed. If it is solvable for x, then you just have to differentiate that with respect to y and then again proceed. If it is solvable for p, that means the previous case, you don't have to differentiate, you just have to rearrange the terms and try to do the integration. Okay, so this is the basic idea. So now here we're going to try to differentiate this with respect to x. So if I differentiate y with respect to x, that's dy dx. We have to use a product rule over here. So we'll have 2p plus 2x, derivative of p would be dp dx. Again another product rule over here, so that would be 4p cube x square dp dx plus 2p to the power 4x. Right, now we have to try to factorize this. If it's possible, try to simplify it as much as possible. So first things first, we need to put p in place of dy dx, right? So in place of dy dx, we need to put p. So what I'm going to do, I'm just going to erase the dy dx over here, and in place of that, I'm going to put a p. Okay. So that means 1p is getting cancelled from both sides. I'm cancelling out the 2. So basically 1p has got cancelled. Let's try to take the dp dx common on that side. If I take the dp dx common, usually this is the easiest way. Try to take the derivative common. Things will get sorted automatically. So if I take dp dx common, along with dp dx, I can take a 2x common as well. I can see I can take a 2x common also. So if I take 2x dp dx common, I have 1 plus, I've taken 2x common, so 2p cube x is remaining. And in the remaining two terms, that means in this term and this term, if I take a p common, I have 1 plus 2p cube x equals 0. So we have easily factorized the thing. The factorization would be 2x dp dx plus p times 1 plus 2p cube x equals 0. Now remember this, once we are able to factorize it, we are only going to work with one of the factors here and not both the factors. In the previous case, when it was solvable for p, we solved both the factors and then finally got back our answer by taking the product of both solutions. Here that's not the case. Here we are only going to work with the factor which involves the derivative term. If we have the dp dx term in this factor, that means we are only going to solve this factor. We are not going to solve this factor. We are just going to ignore it because that part is not going to give us our general solution. Okay. So remember this, the factor which involves the derivative term, dp dx term, we are going to solve that, not the other factor. Okay. So that means right now we are going to consider 2x dp dx plus p equals 0 and ignore the other factor. Okay, so that would be, now we can separate out the terms. 2x dp dx equals minus p, so 2 dp upon let's keep the 2 dp upon p equals minus dx upon x, and we can integrate both sides. So if I integrate this, I'll be having 2 log p equals minus log x plus log c, right? So now if I try to simplify this, I have log p square equals log c upon x. If I get rid of the log terms, I have p square equals c upon x. So that would mean p equals plus minus under root cx, c upon x. But remember, this is not our final answer because p means dy dx. So we still have a derivative left because p itself is a derivative, it's dy dx. So obviously this is not our final answer. Now the major mistake that people do from here is that they write dp dx as dy dx, then again try to solve the remaining differential equation. Well, we don't have to do that. Now the moment you've got the value of p exclusively, just take this value of p and go back to the original question, and place the value of p wherever you can see it. The moment you've placed the value of p in the original question, that is your general solution. That's it. We don't have to solve this differential equation further. Remember this. This is the important part. So we don't have to solve this again. Just the value of p, you take it and you put it back in the differential equation. But please don't forget the plus minus sign. Don't ignore it. Don't just take the positive root over. Take both positive, negative and solve along with that. So I have the differential equation y equals 2px plus p to the power 4 x square, y equals 2px plus p to the power 4 x square. So I'm going to put the value of p in its places. So I have y equals 2x and p would be plus minus under root c upon x plus p to the power 4 would be, so in p to the power 4 the plus minus would get, the minus would actually get absorbed. So we'll be having c square upon x square into x square. So the x square gets cancelled. I still don't want the plus minus to be written in this way. So I want to get rid of the plus minus by doing a whole square. So let's try to arrange it. Let's bring the c square on the left side. Y minus c square is equals 2 plus minus 2x under root c upon x. Now if I do a whole square on both sides so that I get rid of this plus minus sign, y minus c square whole square equals 4x square c upon x. So one x will again get cancelled right over here. So y minus c square whole square equals 4cx, and this is our general solution. Okay, so we have got rid of the plus minus sign so that the answer looks clean enough, right? So let's take a look at another question. So again, you have to decide whether it is going to be solvable for p, x or y. First of all, there is no x term, so definitely not solvable for x. There are terms for p which involves higher powers, so expressing it as p as a function of xy would be rather difficult. Instead, I think this will be easy to write y in terms of the remaining variables, right? So here what I can do is e to the power y equals p cube plus p. If I take a log on both sides, so I have y equals log p cube plus p, and that means I have got y as a function of the remaining variables. So definitely this is solvable for y. Now the moment you have understood this is solvable for y, either you can keep on doing the differentiation with respect to x from here on, or you can do the derivative right from the original question step. You have to decide which is easy, right? So this is a little bit not easy because a logarithmic term is here. So doing the derivative of logarithmic term would involve fraction, then again simplifying that. So once we have understood that yes, this is solvable for y, erase of the stuff and again start from the question by treating it as solvable for y. That means differentiating both sides with respect to x. What is the, whichever is the rule, right? So I'm differentiating with respect to x because I have already understood that this is solvable for y. So the process for that is differentiating with respect to x. So if I differentiate this with respect to x, I will have e to the power y into dy dx minus 3. Let me take those terms on the right side. So 3 p square dp dx plus dp dx, right? Again, dy dx means p, so I have p to the power y equals 3p square dp dx plus dp dx. Right, now we need to factorize this, keep the derivative terms separate. So what we can do is, if I take a dp dx common on the right side, I have a 3p square plus 1, and on the other side I have p to the power y. So obviously here my derivative is dp dx, so that means my variables are p and x, right? My variables are p and x, but I have a variable in terms of y also, so that is going to create a problem. Okay, right? I cannot have 3 variables, I won't be able to integrate. I need to have only 2 variables so that I can separate the variables and integrate. So y is my problem right now. So whichever variable is extra or creating the problem, substitute it back from the original question, right? So I can substitute the value of e to the power y from the original question, right? So in place of e to the power y, I can put p cube plus p, right? So if I do that, I am having dp dx 3p square plus 1 p into e to the power y is p cube plus p, right? And so I'll just continue on this side. So I have dp dx 3p square plus 1 equals, if I take another p common, so I have a p square plus 1, right? So now I have only p and x as variables, there is no y. I can separate the terms and start my integration, right? So what I can do here is 3p square plus 1 upon p square times p square plus 1 equal times dp equals dx. So now we have to integrate the left hand side. Okay, how can we integrate the left hand side? We'll do something with the numerator term. Let's write the numerator 3p square plus 1 in this way: p square plus 1 plus another 2 times p square, right? Whole divided by p square times p square plus 1. So then I can divide this term and this term separately by the entire denominator. So that means if I divide this term, then the p square plus 1 gets cancelled and I have a dp upon p square. For the second one, the p square gets cancelled, so I have 2 times dp upon p square plus 1 equals integration dx. So now it's easy to differentiate these two terms. So if I integrate 1 upon p square, that's minus 1 upon p, 2 times dp upon p square plus 1, that would be tan inverse of p equals x plus some integrating constant. Now what were we doing? We were finding the value of p in terms of x and then substituting it back in the main equation. But now that's a problem here, because p is in such a place that from here we are not able to write p as a function of x. We are not able to do this. We were able to do this in the previous question. We got the value of p as a function of x, we substituted it back in the question and got our answer. But here we are unable to do that because of the nonlinear nature of p, or how it is arising in the solution. So when we are not able to do this, then the process for writing the general solution is, remember this, we can write the general solution as whatever we have got over here. We need to write x in terms of p first. So x in terms of p is 2 tan inverse p minus 1 upon p minus c. That's x in terms of p. And also we need to write y in terms of p. Now how will we get this y in terms of p? That will come from the original question, right? From here. So let's just do one line calculation from here. So we have e to the power y equals p cube plus p. If I take a log on both sides, I have y equals log p cube plus p. So this is y in terms of p. Okay. So y in terms of p, we are getting it from the question. So that's y equals log p cube plus p. Now together they represent the general solution. Okay, together they represent the general solution, and we need to mention where p is a parameter. Okay, that means it's a parameter which we are unable to get rid of because of the non-linear nature of the solution. If they were not so non-linear, we could be able to remove the p by substituting them. Since we are unable to do that, so we'll write both the equations, x as a function of p, y as a function of p, and together they will represent my general solution, p being the parameter which we are unable to get rid of. Okay, so together they represent the final answer, right? So this is two ways of doing the solution. Either we are able to substitute the p in the question and get the answer. If we are not able to substitute, then we are writing these two equations and saying that these two represent the general solution. Okay, let's take a look at another question. So again, we have to decide whether it is going to be easy to solve it for x, y or p. Okay, so first of all, we can definitely solve it for p because we can see it's a quadratic for p. Okay, it's a quadratic for p, so that means solvable for p is possible in this case. Okay, solvable for y will not be possible because lot of non-linearity is present in the y variable. Y square multiplied with a log y. So that means we won't be able to express y as a function of x and p. This won't be possible. So this will not be solvable for y. But again, this can be solvable for x because we have just one x term, right? We have just one x term. So we can very easily write this x and keep everything else on the right side, and it will be of the format of solvable for x. So that means we can solve this for x also, solve this for p also. Whichever one is easy for us. So solving for p will not be so easy because it's a quadratic, we have to do a factorization or Sridharacharya. So rather we will choose to solve it for x. Okay. So that means, okay, now once we have understood that yes, this is solvable for x, no need to write it in the form as x as a function of y and p. No need to do that. We will directly start from the question. Now what is the process to solve it for x? We have to differentiate it with respect to y. Okay, whenever something is solvable for x, you have to start by differentiating with respect to y. Okay, and you need not to bring it in this format. You can directly start from the question line. Okay, so let's differentiate this with respect to y. So if I do a product rule over here, I'll be having 2y log y plus y squared times 1 upon y. Now let's be careful. There are three variables over here and I have to differentiate with respect to y. So first I have to differentiate with respect to x, then y, then p. So at first, if I differentiate with respect to x, I will have dx upon dy, y and p remains. Then I'm differentiating with respect to y, so x and p remains. Next I'm going to differentiate p with respect to y, so I have xy dp dy. And finally derivative of p square, that would be 2p dp dy. Right, now we already know that dy dx means p, so that means dx dy means 1 upon p. So if I place this value right over here, dx dy as 1 upon p, so that means 1 upon p and the p term gets cancelled. So let's simplify this. 2y log y, 1y getting cancelled over here, so plus y equals y remaining that side, which is going to get cancelled, and the remaining terms are xp plus, if I take dp dy common, then I'm left with xy plus 2p. Let's simplify this and we are going to get 2y log y minus xp equals dp dy common xy plus 2p. Now again we can see here that the required variables are p and y, but we have some unnecessary variable x over here and x over here. These two are my unnecessary variables. I need to get rid of that, otherwise I won't be able to integrate both sides. So what I can see is that I will get the value of x into y from here and substitute it right over here. Similarly, I'll get the value of x and p from here and substitute it right over here and get rid of the x. Then maybe we'll be able to integrate both sides. So let's see what we can do. If I try to find out the value of xy from here, xy, that would be y square log y minus p square upon p, right? And similarly from here, if I find out xp, that would be y square log y minus p square whole upon y, right? So if I substitute these values over here and over here, then let's see what we're going to get. So 2y log y minus xp would be y square log y minus p square upon y inside a bracket, and dp dy x into y, that will be y square log y minus p square upon p plus 2p, right? So now let's simplify this little bit. If I do an LCM over here, so I have 2y square log y minus y square log y plus p square upon y, and on the right side y square log y minus p square plus 2p square upon p. So I can cancel out some terms over here, and we are going to get y square log y plus p square upon y equals dp dy y square log y plus p square upon p, and I can see the numerators are getting cancelled, right? So now we have a very simple differential equation, dp dy equals p upon y, right? So that means dp upon p equals dy upon y, and we can easily integrate this on both sides, and that would be log p equals log y plus log of some constant. So let's bring the logarithm terms together. So log y into c, and that would mean p equals y into c, but here I have got p in terms of y, so I can substitute this back in the differential equation and get my answer, right? If I was not able to find the value of p from here, then again I would have to write two equations and state that these two represent the general solution, right? But here that's not the case. I have got the value of p as yc, so that means if I go back to the question, then what I can say is that in place of p, I can put yc. In place of p, I can put yc, which I have got. If I plug this over here, then I'm going to get y square log y equals xy into yc plus yc whole square, which means y square log y equals xy square c plus y square c square, and this is my final general solution. Okay, so I hope this makes sense. Let's take a look at another question. So here again we have to decide whether solvable for p, y or x, which is easy. Obviously we can see there is just one term of x, that means x in terms of the remaining variables is an easy way to express. So that means we are going to treat this as solvable for x, right? Now let's start with our usual process. We need to differentiate this both sides with respect to y. So derivative of tan inverse would be 1 by 1 plus p square with respect to y. So dp dy equals dx dy. We need to do a division rule over there, u by v. So that would be a 1 plus p square into derivative of p, that would be, let me write it in the next line, 1 plus p square, derivative of p would be dp dy minus p into derivative of denominator would be 2p dp dy whole divided by 1 plus p square whole square, right? Now again dx dy, this would mean 1 upon p. So if I substitute that right over there, I will get 1 by 1 plus p square dp dy equals 1 upon p minus, let's take the dp dy fully common. So if I take dp dy common, and I can see I have a p square over here and a minus 2p square over here. So that means it would become 1 minus p square by 1 plus p square whole square, right? So what I can do is I can take the entire dp dy common. So if I take 1 by 1 plus p square into dp dy common, this term is already present in the left side, so that would be 1. If I take this thing common from these terms, bring it on the left side and take it common, then the terms that will be remaining will be plus 1 minus p square upon 1 denominator factor will be remaining, which is 1 plus p square, right? And the 1 by p remains as it is. So if I do some simplification over here, 1 by 1 plus p square dp dy, if I do an LCM, I'm going to get 1 plus p square plus 1 minus p square by 1 plus p square 1 upon p, right? The p square gets cancelled and I'm left with 2 times 1 plus p square whole square dp dy equals 1 upon p, right? So here I don't have any unnecessary variable x present, only p and y is present. I can separate the variables and do my integration, right? So I'll just separate the variables. 2p dp by 1 plus p square whole square equals dy, right? I need to do some substitution over here. What I can do is 1 plus p square, I can substitute that as z, so that means 2p dp would be dz. If I do that, 2p dp will become dz, so that means dz upon z square integration dy. So this would be minus 1 upon z equals y plus constant. Now z means 1 plus p square, so I will have y plus, taking this term on the right side, so 1 by 1 plus p square plus c equals 0. Okay, so now what I can do is I can find p in terms of y and plug it back in the equation. But finding p from here, I think it's a rather difficult task. Easier one would be I would just keep this expression as it is, and also I would write x in terms of p, which I can get from the question, right? X in terms of p, I can get it from the question. That would be tan inverse p plus p by 1 upon p square. So I can get x as tan inverse p plus p by 1 upon p square, and together they represent the general solution, right? So I could have found out the value of p from here separately and plug that back in the main given question and get my answer. That's one way of doing it. But if finding p from here takes little time, so what we can do, we can just keep it as it is, write x in terms of p from the given question, and together I can say they are representing the general solution. Okay, so that's it in this video. In the next video, we will be solving a particular case called Clairaut's form. So see you all in the next video. Thank you for watching.